Bonjour, thank you very much for this it's a great pleasure for me to be here, and it's a great challenge for me to talk for more than 1 hour. And even though I have so much time, it's difficult to make an introduction to quantum mechanics in 65 minutes. I'm not sure it's even possible. But I will try to start in such a way that even people not working in quantum mechanics, not interested so much about bosons, fermions, quarks, and baryons, how they do interact, will understand something, because in fact we are going to work only with vectors and matrices. So if you know what a vector is, matrix, perhaps eigenvalues, it's perhaps enough. First, let me quote a senior Polish scientist working now in Mexico, Bogdan Mielnik, who many years ago, some 50 years ago, contributed to this field a lot, and later on he wrote such a nice statement. In short, if you look at the physical theory from a large distance, so you don't see any details, the one thing you might notice is a structure of a convex set. You see, there's a geometrical statement, something about convexity. Indeed, we are going to discuss space of quantum states, and I will emphasize it many, many, many times. It will be a convex set. So by the way, he is still alive, he is in Mexico, so Mexican colleagues confirm he's doing fine, yes? Well, what is a quantum state? First, we'll discuss pure states. So, states, in fact, it's just an element of the Hilbert space. However, I was told that mathematicians somehow are not so much satisfied with our notation we are going to use. So therefore, let me be very specific. So V is a vector, like Z1, Z2, up to Z, let's say capital N. It's just a vector. And this vector, we have a pleasure to use such a notation. It's a Dirac notation, it's ket. So we assume that it belongs to the Hilbert space, complex Hilbert space. Let's assume it has n dimensions. N will be arbitrary, for instance 2, 3. Here you see the simplest case n equal 2. It could be infinite. Very often it's infinite, but for the purpose of this talk, it is simpler. I will basically restrict my attention to the case where n is finite. Now we also use such a notation. This is bra, this is ket, and this is, well, basically it is the vector which is transposed and conjugated. So you can say it's in principle psi star. So this is vector, another vector, so of course this object, it is, you multiply vector like this, you get a number. So this belongs to it's a complex number, it's a scalar product. So we can say this is in standard notation psi phi. So we use this for a scalar product, and you will also realize if we multiply vectors like this, well, this is now what? This is a matrix, because you multiply such a vector with such a vector, it's an operator. So this is a matrix. And in particular, let me use such a notation. P psi is a projector onto the state psi, so it is equal to P psi square, and it's positive as a projector operator. So I hope, well, this notation at the very beginning, it seems strange, but it's useful, and in physics somehow we use it every day. So for instance, this is the scalar product, and this is the condition that we basically assume our states are normalized. So basically the only assumption we are doing that psi is not equal to 0, then you can always rescale the vector. Its length is non-zero, so you can assume that the vectors are normalized. In fact, our states are not elements of the Hilbert space. They are equivalence class, because we assume that we identify states which differ by a complex phase. So alpha is phase, e to I alpha is a complex number, unimodular number, so basically it's an equivalence relation. We identify such objects, so in fact the space of states is not exactly the Hilbert space of vectors, it is the space of those equivalence classes. And now it's easy to see that in fact it's nothing else as a complex projective space, one dimension. So it has one complex dimension, so two real dimensions. Well, let's check again. We have here two numbers, two complex numbers, Z1 and Z2. They are complex, so four parameters. But because we assume they are normalized, so there's one constraint, and one parameter goes away because of this phase, we have 4 minus 2, it's two-dimensional manifold. And it happens to be just a standard sphere. You know how a sphere looks like, sphere as a sphere, so this is also a sphere. And it is isotropic. Basically, it looks like a sphere. No points are distinguished. However, if we want to work with such a space, it's better to assume we have a basis. In informatics, we often use 0 and 1. They are orthogonal. So in our notation, we write that states indexed by numbers so let's check how the notation works. This is equal to 0, they are orthogonal, and in general, for a basis, orthogonal basis, we write like this. So I, j index different states, and usually we start counting that I goes from 0 to n minus 1. So you can have many different parameterizations, but if you choose the following parameterization, because we identify objects which differ by a phase, you can multiply entire vector by a phase, ensuring that the first component is real, the second component is complex, and now if you choose such coordinates theta over 2 here, e to I phi, it is just to assure that the coordinates here, each point corresponds, each state corresponds to a point on the sphere, and with this parameterization you see that theta and phi have geographical meaning. They are latitude and longitude of a point on the sphere, so the word geometry can be taken literally. The space of all states for n equal 2, all pure states, is just like a sphere. So I discussed this with the Greek expert. Geometry is measuring the earth, so here geometry, we really can treat the space of all states like an earth. So the key feature in quantum mechanics is that you can take superpositions. What is superposition? Well, of course, it's clear that you can add vectors. Here we add vectors, and at this picture, let's assume this is 0, this is 1. So 0 plus 1 forms this point at the sphere, and it's sometimes called plus. 0 minus 1 is, of course, orthogonal. And such states are non-classical. In classical world, or you have head or tail, but you hardly have a coherent superposition of heads and tails. Let me emphasize one thing. In classical case, you can have with probability 1/2 head, probability 1/2 tail. So this would correspond to a mixture, convex mixture of 2 points, which will be the point inside the ball. This is classical mixture of 2 points here and here. And quantum superposition is not a mixture inside, but it is a point which also belongs to the sphere. So if you rotate it, it is still at the sphere, it is a pure state. So this is the key difference between quantum theory and classical. By the way, if you have any questions or I said something wrong or not clear, please interrupt me in any moment. Yes? Yes, okay. Yes. An observation yes. Either zero, either zero. Yes, if you have a measurement, exactly. So I will come to this point maybe later, but if you want a classical observation, it means in a sense you have a projection onto some axis. If you make a projection onto this axis, then you are exactly right. If you project this point on this axis, it will just go to this point, and then it will be indistinguishable from the mixture, quantum, classical mixture. However, if you make a projection at this axis, of course it's a pure state, so with probability 1, it will give this result. Thank you. Well, Now, to discuss geometry, you need to introduce some distances. Here, by the way, this was the case n equal 2. For larger dimensions, the space of pure states is not a sphere anymore, but fortunately is a complex projective space, Cpn minus 1. So if you know geometry of complex projective spaces, it helps. Of course, we know there's a kind of, again, isometric manifold. No points are distinguished unless you, for instance, introduce a basis. So it has 2n minus 2 real dimensions. For instance, if n is equal to 3, classically you would have probability simplex. You will have like 3 points, 0, 1, 2. And here those 3 points, so there are 3 pure classical states if n is equal to 3. And now we embed this triangle, a simplex, regular triangle in, let's count, 2n minus 2, it is equal, let's say n is equal to 3, so it's 6 minus 2, it is 4-dimensional space CP2. So it is 4-dimensional space of all pure states, which, for instance, includes those 3 orthogonal points. And now, one option is to use the standard metric, like geodesic metric, on this space. It's sometimes referred to as a Fubini study distance. Well, it is just a function, arbitrary or reasonable function of this scalar product. Now look, this is a scalar product of 2 states. It's a complex number. So, okay, we take absolute value of it. And now look, if those 2 states are the same, then they are normalized, so scalar product is 1, arc cos of 1 is 0, so the distance is 0, as it should be. In physics, which sometimes assumes something is not static but dynamical, changes in time, so there is a Hermitian operator we call Hamiltonian. So to get a dynamics, we get a unitary operator, just raising it to the power. T plays the role of time. Of course, there is something like h bar, but it's assumed we work in such units that h bar is equal to 1. Anyway, this is an interaction operator. This is an evolution operator which is unitary, and acting with this unitary operator on a psi state, we get what? Another state, another normalized state. So the unitary evolution is nothing else as a rotation of the entire object. For n equal 2 is just standard rotation of the sphere. For higher n is rotation in higher dimensional space, which seems to be very simple, but it's not so simple, because the number of dimensions could be high. Let's look at the scalar product. So of course the scalar product, let's transform by u psi into psi prime, phi into phi prime. Let's observe that the scalar product is constant. So under unitary evolution, the scalar product is constant, so this distance is of course preserved. So you see, if you have unitary evolution, it's just an isometry, like standard rotation, with respect to any standard distance. Standard distance will be a distance which is a function of this overlap. So I entered this field many years ago, working on dynamical systems, classical dynamical systems, and quantum chaotic systems. You can ask how to quantize them. And there was a very fashionable field of quantum chaos, which basically now poses the question, what happens if you go with n to infinity? It's kind of classical limit, and there is a kind of paradox, because all those quantum evolutions are isometries, and of course if you have isometry, there is no exponential divergence of trajectories. What is typical for classically chaotic systems which do exist. So the clue is that those limits t to infinity and n to infinity do not commute, and somehow this is the reason that those paradoxes can be solved, and somehow nowadays we know much more about classical limit of quantum theory, but I will not discuss it too much now. So let me tell you that I enjoy this conference very much, and to make kind of connection to the issues discussed earlier, I decided to add something here. I was not planning to discuss Monge today here, but maybe you recall, those of you who were here first day, it was a lot of said about Wasserstein distance and Monge-Kantorowicz metric. So it is not generically, people working in quantum theory are not so much enthusiastic about it, but I am, so I'm pleased to mention it. And it's possible also to consider so-called non-standard distances in the space of states. So now you know what is the space of states. Pure states form complex projective manifold, and we'll return to the standard distances, which are unitarily invariant. But here I will just mention, I think, an interesting idea of Monge distance. And to define such a classical, you will see why you can call it classical distance, which is not unitarily invariant, we need a notion of coherent states. So they are very often used in physics, but also in mathematics, they have some sense. There are many different definitions, like harmonic oscillator coherent states, displacement operator coherent states, minimum oscillator and mean coherent states. In mathematics, there are group theoretical approach of Pirogov. But for independently what definition you use, for any classical point x of the classical space, so like phase space, you define such a corresponding coherent state, for instance, by distinguishing a single state called vacuum, a reference state, and taking this translation operator, and having such a, let's assume this is just flat plane, and at each point, okay, let's assume this is a Gaussian. So I have here one Gaussian, and then by displacement operator, I can put it in different places, so I have a family of coherent states. And now, one can represent such a state just by its projection in the basis of coherent state. Of course, it's not a standard basis, it's over complete basis. So this is sometimes called in physics Q semi-distribution or Q function, but it's very simple. This is for pure states, for mixed states is something like this. So if you have now two different states, for one state you compute one probability distribution, for another probability distribution, and now the distance, Monge distance between quantum states, in general they can be mixed. It is just Monge distance, or if you prefer, Wasserstein distance between corresponding probability distributions. So maybe you recall how it was organized. You have initial distribution, final distribution, and you want to minimize work, but not against gravity, only displacement, total displacement used to transform one distribution into another one. In general, it's a complicated problem. In some cases, it can be solved. For instance, if these distributions have the same shape, like this is very simple to solve it. Because then you just need to make a transport from one place to another. And the distance will be, if the shapes are the same, it is just the classical distance. So here, you see why we can call this distance classical, because then, if you take two coherent states, they have the same shape. They are localized in points x and y, so the Monge distance between them is nothing else as a distance between 2 points they are concentrated. So it is a nice example that those ideas which are interesting can be also used in quantum theory. And then later on we also discussed quantum states, Monge distance on the sphere. If the phase space has a kind of topology of a sphere, and we use so-called SU to generalize spin coherent states. But I will not discuss it any further. If you have no questions, let me now go back to the case of standard distances. Standard, I mean unitarily invariant. But I will now go to the more general setup. I will now discuss mixed states. What is a mixed state? We have density matrices. It is an important notion, so I will write it here again. Our definition of the space of mixed states of size n, it is the set of all matrices ρ which map Hn into Hn. Now, they are normalized, trace ρ is equal to 1. They are Hermitian and positive. This is it. It's a very simple notion. We only study matrices. They are Hermitian of size n, positive, and somehow the fact that they are positive, as you know, it is a bit tricky, because if you see a matrix, if you are not an expert, you might not see whether it's all eigenvalues are non-negative or not. And they are normalized. So what it means? It means that sum over let's say, m from 0. I use this notation from 0 to n minus 1. It is equal to 1. We can also call it sum over m pm. So p is just a real number because the matrix is Hermitian. At the diagonal, we have real numbers. And this p can be interpreted as a probability. So in a sense, look, let's take a simplest possible matrix, the case n equal to so I will write such a matrix P 1 minus P. So let me put here Z, and here I have to put what? It is a Hermitian matrix. So I need to put here Z bar. And of course, P is what? P is not negative, and P is okay. So P belongs to 0, 1. And so you see, this is like probability vector. But there are those numbers Z, and look, they cannot be too large. Why? Because we assume that the matrix is positive, so then it means that Z square, just easy to check, Z square is what? Is smaller than P1 minus P. And those numbers are probabilities, sometimes called populations, and those are, I will denote it, coherence. Those numbers are called coherences. So now look, the procedure or some process in which those numbers disappeared, you can easily guess, it's called decoherence, and after decoherence those numbers can go to 0. What you will get a classical probability vector. So in a sense, what I'm discussing is something which is a special variant of probability theory, a generalized probability theory. In probability theory, we learned about it a few times. We discussed simplexes. Geometrically is a simplex of probability vectors. So here, of course, our set of all states, it has to contain this simplex. In the case of n equal 2, the simplex is very simple. You have 2 points, 0, 1. So the simplex is just the segment. In the case n equal 3, the simplex is, of course, this triangle, and the set of mixed states contains this triangle. So, from this point of view, quantum theory, if you are, again, not interested too much in baryons and mesons, it's just like extended probability theory. If you like probability theory, you don't need to go into physical details. You only have to assume that, well, it's a standard probability vector, but enhanced in such a strange way. We have already not a vector but a matrix, and we want to understand first what is the structure of the set of all possible states. So here this is a mixed state, so I want to understand the set, how this set of all density matrices looks like. Are you with me? Is it fine? So look, I have here a very simple model. So the set of classical states for n equal 2 is just heads on tails, so just 2 points. To have probabilistic mixtures, we can have entire segment. So segment interval between 2 points. So the quantization procedure basically allows, so this corresponds to those 2 numbers which sum to unity. So the quantization means we embed this vector into a matrix which is positive, or in other words, we allow for those coherences, for appearance of those density matrices which do not correspond to classical states. So in some sense, what you can do, you can say, well, I will, oops, sorry, it didn't work so well, but you can imagine, well, I was perhaps a bit nervous now, so I spoiled my balloon, but you can guess what should happen. I should blow the balloon. I will see whether it works. If it has a hole, it's even better for my purposes. So, well, maybe it will work still. So quantization looks like this. Okay, this should be a quantization, but this is a quantization, look, under a strong decoherence. This is a very realistic model. Because if you even achieve quantum state, if you wait like milliseconds or microseconds, it will decohere to the classical. So in fact, maybe the times of decoherence times are different, but still, the fact that there's a hole inside, I will try again, it is even good for us, because it means that classically we have a standard set of classical states which can be embedded in the larger dimensional object, but those effects are fragile if you, physically, if you allow any interaction with the environment. The quantum state is likely to decohere or to be transformed into a classical state. So this is kind of with balloon, a model of decoherence. You make it, this is a quantization, you quantize, and then you do nothing, you wait for a while. Because of interaction, it somehow goes back to the classical state. This is the model of decoherence. Okay, so decoherence is, you see, very strong here. So, we are going to discuss this set, and we would like to know, to understand properties of this set. In short, we'd like to know how it looks like. But how it looks like also depends somehow on the choice of the metric or geometry. And here, there are, of course, many, many different distances. I will mention some most important. This is Hilbert-Schmidt distance. Of course, its name is simple. It's just distance is related to the Hilbert-Schmidt norm of the difference of two operators. So trace of rho minus sigma square and then square root of it. And then the very simple, similar definition of trace distance. Now this is the absolute value of the operator, so square root of a times a dagger. They're of course not the same. And there's another interesting object, it's called Buhr distance or Buhr's distance. It is defined via such a quantity which is called fidelity. Now look, it's a bit strange definition. Sigma and rho, they are quantum states, they are positive. So it's fair to write such a square root of rho. This is a well-defined object because it's a positive matrix. And now this is also a positive matrix. You can take square root of it, you can take trace, it looks ugly. You don't even see it's symmetric. But it is. It is symmetric. You can write it in this way. By the way, there are some different variants of this definition. Anyway, for any two matrices, you can compute such a number, plug it here, and this is the definition of the Buhr's distance. And there are many, many of those distances. And then, if you ask me which is the best, well, the answer is basically there is no best choice. Each of those distances has different advantages or disadvantages. For instance, Hilbert-Schmidt is just simplest, it's just Euclidean. If you take standard Euclidean geometry and take 2 points, let's say, inside this ball, then the Hilbert-Schmidt distance is just Euclidean distance. By the way, let me repeat it again. The space of pure states is just a Bloch sphere, and space of mixed states is convex combination of all extremal points. So what is the convex hull of a sphere? A ball. So Bloch ball is full ball, contains mixed states. At the boundary, it has pure states for n equal 2. And maximally mixed state, it is just the identity matrix. Let me write it here explicitly. So let's call it rho star is equal 1 over n, so identity, rescaled identity. It corresponds just to the center of the ball. So this is with respect to the standard Euclidean distance or Hilbert-Schmidt distance. And as you see, of course, any choice of the metric will determine how the space of states looks like. Well, there are many properties, many questions you can ask. For instance, you can ask a question whether a given metric is Riemannian or whether it's monotone. Monotone means if you have a quantum operation, so technically so-called completely positive trace-preserving map, so any reasonable operation, transformation of the space of states, then you wish to require that this distance will not grow under the action of psi. It's called monotone. And it happens that Hilbert-Schmidt metric is of course Riemannian, it's related to scalar product, but it's not monotone. Trace metric is not Riemannian but is monotone, but Buhr's metric has both properties, it's Riemannian and monotone. So you might think this is a good idea to use Buhr's metric. However, there is a theorem by Morozova and Chentsov from the 90s which shows that there is not only one matrix like this, there are infinitely many monotone matrices, metrics. So this is a kind of good news or bad news, if you wish, because this is distinguished, but not so much distinguished. It is somehow distinguished, and it's used in problem of distinguishability of quantum states. To show you a difference, let's again return to the case n equal 2. Yes?
What is the quantum operation phi?
Yes, so I mentioned a little bit. Okay, I will return to it later. I told you it is a completely positive trace preserving map. So it is a map such that it preserves the trace. Basically, it maps the space of states into space of states, with an additional argument that if you consider composed systems, it is also true. Okay, so there is, okay, I will come to this later. So, in this, if you look at the Hilbert-Schmidt metric, the space of mixed states for one qubit is just a ball. You know this picture very well. So you have pure states here and maximally mixed inside. However, if you use Bour's metric, something strange happens. Basically, the space of mixed states forms a hemisphere, but hemisphere 1/2 of S3. This is not so easy to imagine. But if you make a cross-section of standard Bloch ball by taking real states, mixed states, it will be just a disk. Now if you take a disk, okay, let's assume this is a circle. Now if you take a disk, a circle, if you blow like this, you get a hemisphere. This is simple. But now, let's imagine we are in 4 dimensions. If you blow strongly in such a ball, you use the 4th dimension, you can blow it in such a way that I can do it here, cannot do it here, that the entire sphere remains at the hyper-equator and the center goes into the pole. Why this metric is advantageous? Because now you can use the Riemannian geometry at the hypersphere, and for any 2 points, it's very nice to show that this Bour's metric is related to a geodesic distance. It's just a geodesic distance at this hemisphere S3 embedded in 4 dimensions. Okay, let's make a short break. How I'm doing with time. So what can you see here? 50. Well, you perhaps will not recognize those characters. There are 2 people talking. I can tell you, they are talking mathematics. Here's Otto Nikodym and Stefan Banach. They are talking at the bench in Planty Garden in Krakow in summer 1916. Maybe you know what happened in 1916. Well, nothing very special. It was just the middle of the First World War. And Krakow was at the, Banach at that time, he was first studying engineering science in Lemberg, in Lwów. But Lwów was taken by Russia, so he returned back to Krakow. He was born in Krakow. And fortunately, by the way, the one guy here with glasses is Nikodym. Banach used no glasses, but it's very important, because fortunately, because of bad seeing, he was exempted from the Austrian army. He was not drafted to the army, which was very good for us. So he was not killed during the First World War, as many others. And he had, of course, he could not study. He was working in the library, in the bookshop, and he was talking with his colleague, Otto Nikodym, and he had no contact to professional math, whatever. I will return to this story soon. So it is nice that we could realize it happened exactly, 100 years ago. So let's go back to the question of mixed states. So here's the definition I will use all the time. The space of all mixed states of size n. We now assume that we use the standard Hilbert-Schmidt, so Euclidean metric. We are looking at this from this Euclidean point of view. So for n equal to, I will repeat it again, we have 1 qubit state plus Hilbert-Schmidt metric, so we have a Bloch ball with all pure states at the boundary. I emphasize again, following Mielnik that the key property is that the set of all mixed states is convex. Well, it is convex because any state is why it's called mixed state. It can be, any state can be represented as a convex combination of projectors onto pure state. So there are those projectors here, there are matrices, and we have convex combination of projectors. And then this set, what is dimensionality of this set? It is n squared minus 1, because we have Hermitian matrices, complex matrices. So, but they are Hermitian, so there's n squared 3 parameters. But because there is a normalization constraint trace is equal to 1, you have n squared minus 1 dimensions. It works, because for n equal 2, we have n squared minus 1, so 3 dimensions. So the set of all positive matrices forms a convex cone. This is like a huge cone, of course it goes to infinity. But now we have a condition trace is equal to 1. This is just this probability. This relates to probability distribution. And this gives us a hyperplane. So now a cross-section of this blue hyperplane and this huge convex cone gives us this set, which happens to be the ball for n equal 2. For n equal 2, the situation is simple. We just have a sphere and a ball. However, let's consider the next case, n equal 3. So this case, classically, we have a triangle, probability simplex. We know it's n squared minus 1, it's exactly a dimensional set. But the set of pure states, so extremal states, is only 4-dimensional space CP2. So now look, 8-dimensional set has 7-dimensional boundary, but only 4-dimensional set of pure states. So this is important. There are some states at the boundary which are not extremal. But this is possible to somehow believe. Look, if you take this triangle, here there is a point at the boundary, which is not extremal, of course. Extremal are only those 3. So now you can ask a question, how this set looks like. So even in the simplest case, non-trivial, so n equal 2 is simple. N equal 3, if you ask me how this set looks like, it's 8-dimensional. I have to tell you, after studying this problem for, let's say, 15 years, I don't know. Well, it is a complicated set, I know something, but I really do not know how this 8-dimensional set looks like. But what I know to some extent, it is how it does not look like. So maybe you know the word, what is apophatic approach? Apophatic approach is to say how a given object does not look like. So for instance, the game we will play is the following. I will show you some objects and ask you why it is a good model how our set does not look like. Okay? For instance, this is the first object. So this is again a model how our set does not look like. So why it is a good model? Have you any ideas? If you ask Mielnik what he said, it should be a convex set. This is a convex set? No. It's not a convex set, yes? I took it from my children as they were young. And now yes, it's a nice object which is not convex, definitely. So again, I visualize how this set does not look like. This is simple. So well, for n equal 2, we knew it's a ball. For n equal 3, it's not a ball. We can assure it's not a standard ball. So again, the simple ball, a strange tennis ball for beginners, is a big one. It's a good model how the set does not look like. Let's see what I have here. Well, this is T, apple T. So this is what like not polygon, polyhedra, polytope. We know it's not a polytope. It's not a cube or something. So it's again a model how it does not look like. Well, what we have here, this is simple. We have a cylinder. Cylinder is better. It has some flat parts and some round parts, which is nice, it's good. So why it is in apophatic approach a good model how our set does not look like? What is missing here? Who has some ideas? Maybe the chairman? Look, on purpose to make it easier, I use some red color to mark some things. So what are the extremal points of a cylinder? 2 circles. So how many? 2 is 2. They are not connected. They are, no. The point is the set of all pure states is not connected. And we know that the set of pure states It's like complex projective manifold which is nicely connected. So again, this is a model how our set will not look like. But we can make a simple trick. Look. What is now? Please have a look at it. So what I make a small change, and now the set is already changed its geometry because now the set of all mixed states is connected. You see? So it's a better model now.
Wow.
Yes, you can please. It's a very simple object. So this is much better model. In some sense, this is almost the best I can find, but it's still not perfect. By the way, if you know how the tennis ball looks like, you know how it looks like. Let's imagine, if you ask a question, how the convex hull of the seam of the tennis ball looks like. You take the tennis ball, you take the seam, and you cut away everything which is outside to take the convex hull. So it looks more or less like this. And, okay, so here it is. So this is a sphere, and inside I have something like convex hull of a tennis ball, which basically you see that you can cut away a lot of the volume. So in a sense, this is one of the best possible models, but it's still not perfect. Why it's not perfect? For n equal 3, there is this triangle, equilateral triangle, because n is 3. This is triangle of classical probability distributions. So it should be embedded inside. And it's not possible to embed this triangle inside in such a way that those 3 corners belong to the seam of the tennis ball. So this is a little better model. We take a triangle and we revert it in a fancy way and take convex hull of it. It's a very special, but it exists, such an object. And at least here you can see that you can inscribe such triangles inside. But in short, as one of my older colleagues told me, the simple answer is because you are showing me 3-dimensional objects. So all 3-dimensional objects will never reproduce all complexity of 8-dimensional objects. So all objects I have in this bag, in this sense, work because we cannot show 8-dimensional objects here. But I want to explain that on one hand, we know a lot about this set. On the other hand, we do not know all these details because dimension goes fast. Now you can ask me, why do I care about this? Well, for simplexes by definition are simple. We know what is a triangle, we know what is a tetrahedron, and so on. Here, those objects you can call it like quantum analogs of simplexes. Because this is the generalization of simplex, that this generalized probability theory takes place in this set. So before you want to discuss dynamics, how probabilities changes, you might wish to understand what is the structure of this set. Well, I will here show you a picture of my city. So this is the Wawel Castle in Krakow and the Vistula River. Well, I will return to this picture soon, but one approach I was following was kind of apophatic, not constructive. Here I will mention a more constructive approach. Let's assume you have a complicated set in 5D. You don't know, you want to study. What can you do? Well, first you can take this object and try to study its projections onto the 2-plane or 3-plane. Or you can cut it and study its cross-sections. Because then cross-sections and projections are easier to visualize. This is simple. So we can also do it like this and study 2D or 3D cross-sections and projections of those states. And we can also study some projections of the subsets of this state. I will refer to discuss separable states later. And here I will use a nice mathematical notion, perhaps it's known to some of you. It's called, in the operator theory, numerical range of field of values. In our physics notation, for any operator A, I define such a set. In German it was Werte Vorrat, so it should be W here. So what it is? This is our state, but it's normalized. So this means, in physics jargon, expectation value of operator A in the state X. So I take A times X is a vector, it takes scalar product. So my set contains all possible expectation values of a given operator. It's called numerical range because if you take Hermitian case, this is the most important for physicists, then those numbers are real, if A is Hermitian, and then it's easy to show that this set is nothing else an interval between the smallest to the largest eigenvalue. Lambda 1, lambda n denote eigenvalues of this Hermitian operator. It has such a spectrum ordered and the range, numerical range, is just a range from first smallest eigenvalue to the largest. Well, we can also discuss this notion for non-Hermitian matrices. So in general, this set is a subset of the complex plane, and there's a famous theorem of Hausdorff and Teplitz, more or less 100 years old, which tells us that this set is convex. It's a convex, always a convex set. By the way, this is exactly the same name, same notion of convexity mentioned by Mielnik, and I will tell you those two somehow the statements have something in common. But let me show you some examples. If you take random matrices of order 6, you have 6 eigenvalues, so red dots denote eigenvalues. If the matrix is normal, it commutes with adjoint, then the nice theorem says the set is just convex hull of the spectrum. So it's just a polygon. But in the generic case, not normal, it's a set which is convex and it contains all points inside, all eigenvalues inside. So are you with me? This is a well-known mathematical notion defined for any matrix, any operator. Well, let's look how it looks like. So for a normal matrix, we have always convex hull of the spectrum. So for n equal 2, we have 2 eigenvalues. It is just an interval. For n equal 3, we have 3 eigenvalues. So this convex set is just convex hull of 3 eigenvalues. It will be a triangle. It's a triangle on the complex plane. This is simple. In the case of non-normal matrices, what is not normal? For instance, this matrix of Jordan is not normal. You see, it's not symmetric. Then it's possible to show that for not normal matrices, this numerical range forms always an elliptical disk with eigenvalues as focal points, and axes can be computed by an explicit formula. It is like 80 years old result. For instance, for Jordan matrix, so 2 eigenvalues are 0, it will be not only an elliptical disk, but a circular disk with radius 1/2. But look, we know that the set of states for n equal 2 is just a sphere. And then if you take a sphere and look for its projection onto a plane, it will be a what? What can it be? It can be only a circle or an ellipse. If you change the projection angle, you can get an ellipse, you see? You can have a disk or an ellipse, and this ellipse can degenerate to an interval. So we can ask a question, what is in common between a set of states and numerical range of an operator? So here I show some numerical ranges. Okay, just this could be considered of some operators as a circular or elliptical disk. And now I will return to my city, Krakow. So this is Wawel Castle from the other side. And the picture is important because it allows us to formulate a mathematical theorem. So this is a theorem of my colleagues Danuta and Krzysztof Ciesielscy. And theorem can be formulated like this. With probability 1 minus epsilon, the bench Banach talked to Nikodem in 1916 was localized in eta neighborhood of the red arrow here. So this is you see concrete mathematical statement, even though the functional dependence between eta and epsilon is still unknown. So look, they were talking together, Nikodem and Banach, and they had no contact with mathematics, and then they were discussing, we know now what they were talking about Lebesgue Integral, which was very fresh and interesting concept those days. And then a professional mathematician, Hugo Steinhaus, was passing by, and he somehow was very much amazed that, look, during the First World War, close to the front, some 2 young guys were talking about Lebesgue Integral. So he could not help overhearing, introduced himself. They started conversation. It was the first time they met. And then they were very much amazed that they talked to a living mathematician. Banach learned what Steinhaus was working on. He worked on convergence of some Fourier series. They met a week later, and Banach already had a solution for Steinhaus, and they eventually wrote the first paper together about this. And all the, let's say, we say now that the story of Polish mathematical school in Lwów started there, because then after the First World War, Steinhouse got a position in Lwów and arranged position for Banach, what was not so simple because he never finished his studies. And he was reluctant even to write PhD thesis and to pass exam. I will show you a book from this library, which is nice, about Stefan Banach, his remarkable life. But we'll mention here only one nice story, that since Banach was not so keen on taking exams to get PhD, there was a plot made somehow against him. So one day Banach was stopped at the corridor of the university and asked, "Would you come to the dean's office? There are some people there with questions about certain mathematical propositions that you should definitely be able to help them." So he went to the office, he found some guys, he was older gentleman he was not aware of. It occurred, there were members of the special commission which came from Warsaw to examine him, and this was the way he passed the exam. This was just the formal exam for his PhD. So I will show you this book, which is nice. It is here in the library. I think it's good to browse it at least. So please pass it through. And so this is the book, which was, there were some biographical materials collected recently in Poland, and now this is the English version of it. Wow, so we return back to basically shadows of some objects. Now look, maybe you recall the story of Platon and his cave. So he said, well, maybe we are just looking at the shadows of some objects we do not understand. Basically, our situation is similar. We exactly do not understand those many-dimensional objects, but at least we can somehow look at the shadows or projections or cross-sections and try to imagine how those objects really look like. So here, for instance, I plotted shadows of a ball, okay, sphere, full ball, or a tetrahedron. And this is basically how we... what is our situation, but we can formulate those issues in a more precise way. Namely, we can connect space of classical states with normal matrices, and if Cn denotes a set of classical states, so just the probability simplices of size n, then the set of all orthogonal projections on the two-plane is equivalent to the set of all numerical ranges of all normal matrices of order n. So if you have a normal matrix, basically you see a triangle, and then interestingly any triangle can be obtained if you take a projection of an equilateral triangle under a certain angle. And now, more general statement concerns now quantum states and numerical ranges of generic, so not normal matrices, and then the set of all possible projections of the set of mixed quantum states onto a plane is equivalent to set of all possible numerical ranges of all matrices of the same size. So now you see that there's a relation between this convexity theorem of Hausdorff-Teplitz and the fact that the set of mixed states is a convex set. So here are some examples for n equal 3. They are just projections of this set. So it's a more constructive approach. We have this eight-dimensional object we don't understand, and we look into the projections of this object onto the plane. So for instance, it can be also a triangle, or it can have, so it has 3 flat parts, or 2 parts, or 1 flat part, or in generic case, it is just a kind of oval. So here, green points denote eigenvalues of those matrices. You can also study 3-dimensional projections, but I think I have to speed up, and then you have a projection of the 8-dimensional bodies onto a 3 planes. So now, this notion of joint numerical ranges, you take basically physically 3 expectation values and ask this rational question. You have 3 measurements, you measure 3 quantities, and you want to know in the space of those 3 measurements where the outcomes might be. Here we assume that those operators are Hermitian. So the point is how to classify those objects, and these are the possible shapes of those objects if you take 3-dimensional density matrices. So in other words, there are possible projections of this set into 3D. So here I should somehow acknowledge the author of those objects. So here is my student Konrad Szymański, who produced such a three-dimensional numerical range using a 3D printer. So you see now, 3D printer can be used to really produce such objects. Okay, so we can classify those shapes, but I think I will not discuss it any longer. Now, yes?
Just one choice the proposition. Yeah, thank you.
Could you speak up, please?
No, because I had not time to
Yeah, sure.
proposition 2.
Yes. Proposition 2 is similar as 1, but here we discuss the set of all mixed states, and we take all projections of the set of quantum states, this set I discuss, and it says that the set of all projections of this set onto a plane is equivalent, similar to the set of all possible numerical ranges of all matrices of a given size. So it's a relation between set of projections and set of possible numerical ranges of all possible operators, so all possible matrices of the same size.
Without normalization, that you are correct.
Yeah, up to rescaling, up to rotation. But geometry is the same. Thank you. And, okay, so in a sense, this theorem summarizes the simple observation. If you take a ball, its projection is only an ellipse. Nothing else can be. And we know for 80 years that for n equal 2-dimensional matrices, every numerical range is either an interval or an ellipse. And we somehow managed to link those two mathematical ideas together. Thank you for asking. So, and now one more remark. Look, the set of states is simple for n equal 2, gets complicated a bit for n equal 3. For n equal 4, 5, 6 is more and more complicated. Why? Because dimensionality grows. Dimensionality goes like n squared minus 1. So if n is huge, you can think it's so complicated you can not say anything about it, because it's very, very complicated as dimensions grows. However, there is one catch, and I decided to discuss it because first day we learned many ideas about theorems related to concentration of measure and Levy lemma and things like this. So let me first ask you how a cross-section of a free cube looks like. Of course, we know it can be a square or a pentagon or a hexagon, but not more, because we have 6 faces. So if you have a cross-section of a cube, you will have not more as 6 sides. So what about the generic cross-section of an n cube? You take n cube in n dimensions and you make a 2-dimensional cross-section, what you will get? So you can get not more than 2n polygon with 2n. But if n is huge, how a polygon looks like? Look like a circle. And I will mention a famous theorem of Dworecki about some results of convex bodies and Banach spaces, by the way, so Banach eventually appears here. So in short, under some technical assumptions that those objects are not too elongated, if you take a generic cross-section of a high-dimensional convex body, almost surely you will get a disk as a cross-section. It's very nice in a bit unexpected statement, and it's related just to concentration of measure. Because if you can try to find a different cross-section like a square. But if you take generic orientation of your plane in many-dimensional space, most likely for any object convex, the cross-section will be close to a disk. And here I will mention a French page when the cubes become round. So become round because if you take cross-sections, they are round. So there are people from Lyon, I think, yes? So here is a similar example. We discuss numerical ranges of random matrices. Gini matrix is such a matrix where all elements are Gaussian, independent. It's not Hermitian matrix. For n equal 10, what you see here, it is numerical range, but you can consider it as just projection of the set of mixed states of size n. So dots are eigen values, and this is this object. You see it's kind of deformed circle. This is for n equal 100. And here is for 1000. So for 1000, you see, it's almost a perfect circle. And the smaller circle of eigenvalues is called Gierko disk of eigenvalues. So this numerical range is a bit larger, but in short, it confirms the statement that the set is so complicated, you cannot describe details. Fortunately, if you take the average property, like average cross-section, you can prove that it's with very high accuracy, it's a disk. So here we could prove it explicitly to make the statement correct, that in the limit n going to infinity, distance between a typical numerical range or such a typical random matrix of size n to the disk goes to 0. And this, of course, relation to the Dvoretzky theorem. It has something to do with the structure of the set of mixed states and their cross-sections. Thank you. Well, so, okay, if I discuss this to my colleagues physicists, they are somehow worried and they are unhappy and bored because they say, where is physics? Well, there's no physics inside. Okay, you can ask now a demagogical question, what is physics? So of course, well, we know if you kick a ball, it will stop at some point. If you buy an ice cream and do nothing, it will melt, especially in Marseille. Yes, you don't need to wait too much. But now look, if you create an entangled state, I will explain what it is, and do nothing, what will happen? You can guess? Nothing good. It will somehow decohere to a separable state, as discussed here. So basically physics is, somehow this is already a physics. Something will happen just because of inevitable interaction to the outside world. So I'm now asked to go back to discuss quantum entanglement in a more detail. And then I will discuss the subset of the set of all states, which are separable states. So let me first start with the simplest case. I have only two subsystems, like A and B. So it's called bipartite situation. And now I treat only pure states. So definitions are extremely simple for mathematicians. A separable pure state is not separable space. Separable in a physical sense, so we can separate two objects, means that you have only a tensor product structure. And entangled state is even simpler. It's any state which is not of the above form. By the way, it's again an apophatic approach. Entangled state is not of this kind. So of course you can guess, every mathematician will know, it's a kind of a simple observation, that typical states will not be of this form. So they will be entangled. So entanglement mathematically means just for pure states, it's not a tensor product. For instance, if you take, again, simplest 2 times 2 problem, we call it 2-qubit system. So dimensionality of the space is 4. You have 1 qubit here, 1 there. And the nice state of Bell, it's called Bell state, which we write like this, 0, 0 plus 1, 1, is not of this form. This is a tensor product, by the way. This is exactly the same as this. So let me write it here again. So notation is like this. 0, 0 is the same as 0, comma 0 is the same as 0. Formally we write A, tensor product 0. B, which means that there is a state 0 of subsystem A and multiplied by tensor product with a 0 of size B. But to make it shorter, we put here comma or even without commas. So you see that, of course, this is not a, this is a tensor product, this is again a tensor product, but together it's a superposition. By the way, you see here a superposition of two states, which is not a tensor product. So this is called a Bell state, and it's really a very, very tricky state. Let's assume, well, you have two dices. Okay, this is a standard dice, again standard dice. Let's assume we have two dices which still fly in the air, and then I will claim that if I will see 6 here, you will also see 6 there. Will you believe me that they have such two dices like this? So they are still flying in the air. Oh, I throw them, they are fair dices. But if I observe what happens here, I will know what happened there. You would say I'm joking or this is cheating. It cannot exist. Of course, everybody knows it cannot exist, yes? So in a sense, Bell states require the same, because if we make a measurement of the first subsystem, if it's 0, we'll know that the second measurement will also, the outcome will be 0. If here is 1, it will be also 1 there. So it's really a very non-classical state. In some sense, well, the subject of this session is correlation. So in some sense, entanglement reveal some very strong non-classical correlations. If you have a tensor product, there are no correlations whatever. It corresponds to independent subsystems. Correlations mean they are, well, somehow dependent, but here entanglement means quantum correlations. It is a sign that those two subsystems interacted before. You can never have any entanglement in physics unless there was an interaction between two parties. This state is also called maximally entangled. Why? Okay, maximally because it maximizes some measures. During this workshop, we use the word entropy very often. So yesterday and 2 days ago, everybody used entropy, so I use it also. Entropy is, of course, very important. Here, instead of Shannon entropy is just the entropy of the probability vector. We use von Neumann entropy, which is nothing else. It is defined here. It is Shannon entropy of the spectrum. Formally, it's minus trace sigma log sigma is the entropy of the spectrum of a matrix. And the definition of the entanglement entropy is the following. For a pure state of bipartite system, we define this partial trace. So partial trace means we take two objects and we average with respect to one object, and what we get is the state of a single object. It could be mixed state. So if you take this state, okay, let me still use some of my time to show that it works. So if you take rho plus equal to psi plus, it is just a projector. It will be a matrix which looks like this. 1, 0, 0, 1. It's a matrix 4 times 4. It has 4 non-zero elements. Why 4? Because you have this state and you multiply by its adjoint. So you have 2 times 4, 4 elements. Now if you consider sigma, which is partial trace with respect to any subsystem, like B here, of this state, rho plus. So partial trace in this case means we take the sum of those two blocks. It is just 1/2, 1, 0, 0, 1. So this is the identity matrix, maximally mixed, so entropy is maximal. So because entropy of the partial trace of this state is maximal, this state can be called maximally entangled, Bell state. By the way, if you take now 4 separable states which form a basis, like 0, 0, 0, 1, 1, 0, 1, 1, and take real combinations of them, for each point like this, you can compute entropy. So here, the colors mean they are lines of isoentropy. Red means high entropy, so entangled states. Blue, separable. Now look, if you take 0, 1 and make superposition with 0, 0, the first symbol is 0. So the entire line is separable. However, if you compose 0, 0 and 1, 1, here the state is entangled, so is this one. So the colors mean entanglement. So this is kind of a map where you see what parts of this simplex are separable, which are entangled. And you see here those two states are really maximally entangled. By the way, this was the cover story of our book, published a few years ago by Cambridge University Press, entitled Geometry of Quantum States. And now I'm very proud to mention there is already a new edition which was published this year. It is extended a bit. Now we discuss also multiparty entanglement. I will not discuss it now. So it's already, it's ready. I have not found yet any errors in the second edition. In the first, many errors. Maybe there will be less. So now let's go to the mixed state. It's a bit more complicated. We already know what the mixed states are. So now the definition is a bit different. The state, mixed state, is called separable if it is a product state, like this. So you see a tensor product of two density matrices, or if it is a classical combination of those. So convex combination of any product states. It makes sense because it means that or I have a product state without correlations, or I have superposition of, combination of those. And then entangled mixed state is any state which is not of this form. Again, an apophatic approach, because if you are given a matrix, you will not know whether it belongs to this class or not. And the key question is how to find whether a given density matrix, like a matrix like this, satisfies this condition or not. It's called separability problem. It is solved only for the case 2 times 2 or 2 times 3. In general, it's still open. How much? 15? Okay. So, in the simplest case, there is a very nice statement which is quoted in literature as positive partial transpose or Perez-Horodetzky criterion. Horodetzky is a pluralist of the Polish name Horodetzky. There was an interesting paper by Asher Perez who proved one statement in one direction, and later Richard Horodetzky with 2 of his sons proved a statement in another direction. So now it's known like pH to power cube statement, which goes like this. T stands here for transposition, so you know what is it to transpose a matrix. Now I assume we have a bipartite system. We can transpose one subsystem or second subsystem of both. So partial transposition means here you transpose, let's say, second subsystem, and you leave first not touched. So what it means mathematically, so partial transpose means you make a transposition here only in each blocks. And then if you also exchange blocks, you would have a standard transposition. So the statement is very simple. You take such a matrix, you perform this partial transpose. So in this case, those 2 elements go here. So I can write it explicitly. Rho plus T, we call it T half. I mean, T2 means second. We exchange second subsystem. It looks like this. This does not change. This does not change at all. However, here I have to swap, make a transposition here. So I get 0, 0, 1, 0, and here 1, 0, 0, 0, because I make the transpose in each block. And now, of course, you immediately see that this matrix is not positive, because this part will not be positive matrix. So this criterion is very simple. It says that if you take this matrix you want to investigate, you perform partial transposition. So mathematically, it's a very simple operation on the entries. You check if it's positive. If it is, the state is separable. And geometrically, well, it has nice interpretation. This is the set of mixed states. Transposition is, in a sense, nothing else as a reflection. But you see, we here have n dimensionality is high. So this is a kind of hyper-reflection with such a hyperplane. So if this is the set, this will be the set after the reflection. It has the same volume, same shape, but reflected. So the criterion of PPT says that if you have a state which belongs to the cross-section of the original set and is partially transposed, so in this blue region, it will be separable. Well, if you consider, again, 2-qubit system, so simplest possible system, you can take spectra and they form, of course, a tetrahedron. You have 4 numbers, they sum to unity, so they represent classical probability tetrahedron. And now you can inscribe inside this tetrahedron a ball. And then it happens, one can prove that if you take any state such that its spectrum is inside this ball, is a maximal ball inscribed in the tetrahedron of eigenvalues, it's also a separable state. So in short, if the state is close to the maximally mixed state, it will be separable. It's close enough. This was basically my first paper on this subject, written, well, started 20 years ago. And here I will just show you, again, a geometrical interpretation. Here's a cross-section of the space of mixed states. So here white means separable states. The darkness is entanglement. Black is very entangled state. White is 0. So this is the boundary of the separable states. This circle is just this image of the separable ball. Here, rho star is this identity matrix. So 1 of size 4 over 4. And now you see that the degree of entanglement can be interpreted as a distance to the boundary, to the separability region. This is the boundary of separability, and in a sense, you can have a geometrical picture that entanglement measures the degree of entanglement is just the distance from the line boundary of separability. However, again, you can ask a simple question, which distance to use? And again, depending on the distance you use, you have different entanglement measures. And again, it's not possible to say, this entanglement measure is better than others so much. Of course, we can have some preferences, but unfortunately, it's not like this that a single entanglement measure is considered to be the optimal. For different purposes, you use different entanglement measures. So here is Banach sitting on his bench close to the Wawel Castle. By the way, I wanted to show, again, to express my surprise that your library here is so good. It contains a very nice volume, first volume of Studia Mathematica, volume of the new journal. It was new in 28, started by Stefan Banach and Hugo Steinhaus, exactly those guys who met there at this bench in 29. And I posed such a question yesterday concerning mathematics and languages, your topic. So look, a very simple question, linguistic question. They edited this new journal. It was not only devoted to functional analysis, but also, and you can ask a question, in what 3 languages they decided to publish papers in this first volume? There are 3 languages. To make it easier, I will tell you, there are no papers in Polish, no papers in Russian, and what's more interesting, pas anglais, no English. So please have a look. By the way, there were not so many readers of this journal so far, but I think it's nice. So I was very much impressed I could find it here. So please have a look, and you will see the answer here. Some of you already know the answer, but it is nice somehow to see that the role of Russian and English was not so big before the Second World War. And now look, so here is the answer to your question. What are the quantum maps? So please have a look. 5?
5.
Yes. So quantum operations, are just completely positive trace-preserving maps. So it means, okay, in short, physically it's better to say we have a state, we assume there is an environment, and there is a global unitary, and then there is partial trace. So in some sense, we allow interaction with environment. So there's a unitary interaction with environment and the partial trace. And this produces all maps like this. They are linear, completely positive, and trace-preserving. And they can also be written in so-called Klaus form. Now look, AI are arbitrary operators, and this form assures that this matrix is Hermitian. And if additionally those operators satisfy such an identity resolution, also trace of rho will be preserved. We wish to have that trace of rho prime is equal to trace of rho, so the operation is trace preserving. So without going to the details, you can describe interaction with environment, also decoherence, by appropriate choice of such operators. So here we discuss a simple model of 2 qubits, and there was a free evolution plus interaction with environment, and there are some different kind of channels, so maps discussed. Here we want only to show you the following thing. This axis is time, it's a discrete evolution in time. Here is entanglement. So entanglement can decrease and then possibly increase again, or it can decay in such a way. We discussed this some 20 years ago, could not understand it so well. We could also observe the following effects. In some cases, the entanglement goes down, stays 0, and potentially revives. It's called revival. But sometimes it goes down and stays there forever. We didn't care so much in our first paper about it. So I had also a paper with the Horodetzky family here. But then Yao and Eberle, 2003, coined a very nice statement, sudden death of entanglement, which basically means that entanglement is positive, goes down, and then stays there forever. It's a very simple observation, but for them it was kind of surprising. So look, without geometric knowledge, it's somehow not so easy to interpret it. But now our interpretation is very simple. Look, this is the set of all states. This is a set of separable states. So to get revivals, it's enough, you have kind of a rotation of the object. So it's easy to imagine. This trajectory goes across the set of separable states. Entanglement vanishes, that goes again here, so it is there, and you see the revivals of entanglement. If the decoherence, so contraction is fast, trajectory can go into a set of separable states and, for instance, stay there forever or contract to some point. And then you observe the entanglement sudden death. And now look, this was the picture we had some 20 years ago, just approximate picture like artist's point of view. And here, this is now a concrete mathematical result. Now here we observe, we take this numerical range, and we have a numerical range with respect to separable states, and we have a concrete trajectory, and we can choose such parameters that exactly our hand-waving arguments are confirmed. So basically here is a trajectory, and then it goes inside the set of mixed states. Now here this is a set of separable states, and you can somehow understand behavior of entanglement and time evolution of entanglement using such pictures, so projecting the dynamics onto a plane. Okay, trying to summarize, I will quote Guillaume and his paper in 2016. So, look, why we care about entanglement, dynamics of entanglement, whether it can be preserved or not. Entanglement is key notion, key resource needed for quantum computation. If you want to do something, you need to create entanglement and process it for a reasonably long time to do something with it. So the question is how fast entanglement will decay, whether it's enough time to do something or not. So in an optimistic picture, there is a classical computing, and well, there are some bridges via noisy quantum systems to the nice higher mountain of universal quantum computing, which is expected to be there, and you hope to may use those bridges to cross to this unknown land with higher mountains. This is the optimistic version. But there's also a pessimistic version that because of the decoherence, those effects, quantum effects, will not be so useful. So in a sense, you can go with a bridge somewhere here, but then this nice picture of quantum computing, huge mountains, also a fata morgana or fantasy, you can never go there. So this is now a key question studied by not only physicists, but also engineers and people working in information science to see whether really quantum computing can be performed. It's not so certain whether the quantum computer will be built. But definitely it is important to study properties of quantum entanglement and how it changes if you take into account interaction with the environment. So, to conclude, I discussed the space of all mixed quantum states of size n, which forms a scene for all screenplays for quantum information processing. In some sense, all algorithms can be considered as nice plate in the scene. So we first want to understand how the scene looks like. And therefore, it's good to learn some more about structure and geometry of this scene. And we are using this notion of numerical range or joint numerical range to analyze projections or cross-sections of this object onto a plane. And then I think the geometric approach is useful to study of quantum entanglement and its dynamics, and it at least allows to explain some effects which were observed before, like entanglement revival or entanglement sudden death, but not understand before. And of course, it's still a lot of work is required to understand consequences of noise, so of the interaction with environment for the future of quantum computing. So this is basically all what I want to say, but then I will show you this bench commemorating the discussion between Nikodym and Banach, which was opened exactly 100 years ago after this discussion took place. The bench is localized close to the Wawel Castle in Krakow. So if you are there, it's good to come to take a picture or sit here and listen what they have to say. Thank you very much.
Okay, thank you, Karol, for this wonderful excursion in quantum world. So, questions?
So you mentioned about noisy quantum systems, especially near the end. So how would you model noise? Do you put classical probability on these manifolds, or?
Well, to be honest, in fact, this is the simplest model of noise, or in physics this, because we have a state, let's say, our dice, and we assume it's coupled to environment. So any noise can be somehow modeled by an interaction with some arbitrary huge environment, and by adding this U, huge U, which is responsible for coupling of the system with the environment. So practically, all those models I discussed here, the noise is described by the choice of Krauss operators, which are arbitrary, with the only exceptions that they have to satisfy this identity resolution. So in fact, all those channels here I discussed, okay, I had no time to go into details, they already describe different kinds of noise, and there are many ways. In fact, we are now studying the space of all those channels, which is also a convex set. It's also more complicated, but in principle, this can be studied. This is simple, but what's more difficult to know which one should be used for to relate with a particular physical context.
In what sense the environment is like? Because here, the environment seems to be any system. In classical thermodynamics, for example, you introduce a hypothesis that this environment is at equilibrium and satisfy asymptotic properties to guarantee that the other one takes none.
Yes. You are entirely right. So look, of course, again, this is a simplification if we assume that here the size of this is finite. Simplest thing I was doing, I took one qubit and another qubit as an environment. But in practice, you are right. You have so-called thermal bath. So you have infinitely dimensional coupling with infinitely dimensional system, and then you need to introduce temperature and statistical assumptions about this bath. So it's much more complicated. But in principle, it can be studied in this way. Okay, but so people work in this field, and as usual, there are many different options to choose, and nobody knows which approach is most promising.
I have a question. So some time ago, together with Stefan Weiss and Andreas Knauf, we studied the problem of maximizing the distance not from the separable states, but from the product matrices, which gives a nice exponential family sitting in that set. So that is the analog of the so-called multi-information, which is of some interest for several people in the audience here. And we have some understanding of...
Which distance? You use Hilbert-Schmidt distance? Or?
No, the Kullback-Leibler divergence.
Okay, sorry.
With respect to the second argument.
Okay. But it's not a distance. It's a semi-distance.
Yeah, I mean...
Technically, yes.
Yeah. Do you think, so some people define the entanglement as you also defined it as a distance from the convex hull of these products.
Yes.
So do you think that the understanding of the maximization problem with respect to the product matrices helps us to understand also the maximization of entanglement?
Yes, a nice question. Yes, it helps, but it will not solve the problem. But I know some of the papers in this direction, and I appreciate them. But you cannot hope that it will solve the entire problem. Because, in short, first question open is separability problem for higher dimensions. Whether a given, so just last picture, if you have the set of all states Mn and the set of separable states here inside, which contains the center. So first question is separability, whether a given point X belongs to the set. This is known for small dimensions. For high, it's not known. And the second, if it's not there, how to estimate this distance? This was the question. There are many different distances, many different options, but in general, it's also not known how to this set. Well, we in principle know the structure of this set, but it's very difficult to, for a given point, to estimate this distance. This is called problem of measuring entanglement. And yet another problem is to relate it to some observable physicists with to experiments physicists do to measure entanglement in real life, which is also doable, but not so simple.
Maybe it seems that the cover of your book has changed to a kind of Borromean links.
Yes, on purpose. Yes, thank you for the question. No, because Borromean beams, I will show it here. This was in fact it's on purpose. Sorry, just a second. Try to be quick. Because Borromean rings are some kind of symbol of so-called GHZ states of three parties, A, B, and C. The idea is if you break one ring, two other rings go apart. This is the idea of GHZ states. So here we want to emphasize with this picture that there's a new chapter about multi-parted entanglement. So entanglement between three or more subsystems. So this is on purpose here.
All right, maybe a last quick question, if you can.
So if you choose a generic quantum operation, is that going to map most points into the subspace of separable states? If I do quantum dynamics with this? So I'm just thinking.
I understand the question. So look, in general not, but there are some special class. It's a very nice question. You can define special class of channels which map all states into the subspace of separable states. They somehow kill entanglement. But of course, it's not a generic feature. It is for special subclass of maps which have this property.
And it's very small inside the space.
Well, yes, it will be small, but also important. Physically, unfortunately, it's physically important somehow. But it's a nice question, yeah. You have a contraction inside the set of separable states. Thank you very much for all the questions.